In this video, I'll talk through the 2022 National 5 Chemistry paper and explain how I would approach each question. First up, question number 1. We're asked about atomic numbers of metals. First thing I would do is go to the data booklet and find which chemical has each of those atomic numbers. You can either use page 4, which has all the elements, or page 6, which has some of the elements. I'm going to deal with page 4 first of all. On page 4, the atomic numbers are the top numbers in each box. We had 1, 33, 45, and 86, which is over here. On this page, if we look down at the bottom, it tells us that the elements below the dark line. On this page, it tells us that the elements below the dark line are metals. When we look at the position of the 4 chemicals in question, only number 45, rhodium, is below the dark line and is our metal, so our correct answer for question 1 would be C. Next up, we're asked about why an atom is neutral. Here we want to be talking about protons and electrons, because protons have a positive charge, electrons have a negative charge, and neutrons have no charge. That means A, C, and D are all incorrect. Only B talks about the numbers of protons and electrons being the same. If the protons and electrons were not the same, that's when you'd have an ion, which may come up later in this paper. Next one, we've got liquid water changing into steam. We're thinking about strong and weak force of attraction, and then whether they're between the molecules or they're between the atoms in the molecule. If we think about a water molecule, when you turn from having liquid water into steam, the gas form of water, you still have the 2 hydrogens connected to the oxygen. What's not happening is we are not breaking the bonds inside of the molecule. C and D both talk about the bonds between atoms being broken. That means those 2 cannot be correct. Next thing we need to think about is whether or not they're strong or weak. These types of bonds that are being broken are called intermolecular forces, and they're a fairly weak form of attraction between molecules. This means that our correct answer would be that weak intermolecular forces or weak forces between molecules are broken. Next question is asking about solvents, solutes, and solutions. Our solute is the thing that is dissolved. Our solvent does the dissolving. And the solution is the mixture that's made. If we're thinking about a salt solution, if you add more salt, which is the solute, it will become more salty, therefore the concentration will increase. If you add more solvent in my salt solution situation, that would be the water. If you add more water, you dilute it, the concentration will go down. C has both them in the correct place, and it's our correct answer. Next up, we're asked about different shapes. Here we're talking about angular. 4 shapes you need to know about. We have linear, where the atoms are arranged in a straight line. Angular, there is a bend in the molecule. Water is a good example of an angular molecule. We have trigonal, pyramidal, which means there are 3 things coming off of a central atom. And there's tetrahedral, which has 4 things coming off of a central atom. A is going to be tetrahedral, which is not what we want. B is going to be our angular. That is our correct answer. We then have linear for carbon dioxide. And then our ammonia is our trigonal pyramidal. Moving on. Here, we're told about a term that's used at higher chemistry, but here we are having it defined for us. It's the measure of the attraction a nucleus has for the shared pair of electrons. When 2 nuclei that have different electronegativity values bonded together, this is described as being polar covalent. The bigger the difference in electronegativity values, the more polar the bond. We have our values here. We're wanting the one that would be the most polar. We're going to want to go back to this line here that says the bigger the difference, the more polar the bond. We have oxygen and hydrogen, so that's 3.4, and we have 2.2. That would be a difference of 1.2. Next up, we've got 3.0 minus the 2.2 for the hydrogen, which is 0.8. Onto carbon, 2.6, 0.2, 0.4. You have carbon, which is 2.6, and oxygen, 3.4, which gives you another 0.8 of difference. Biggest value in this case would be A, the OH bond. Moving on, we then are thinking about electrolysis of copper chloride, and we're asked what would happen at each electrode. Here we run the electricity through the compound, and we're going to split it up back into its original elements. If we have copper chloride, we're going to split that up into copper and chlorine. Copper is going to appear as a solid, and chlorine is going to appear as a gas, as little bubbles. You may have done this experiment, it smells like a swimming pool, and the copper has been produced. We need to then decide, well, which electrode will these appear at? A couple of options for this. One thing we could do, if we go to page number 6, we can see that copper as a metal will exist as a positive ion. Our chlorine, because chlorine, to get a full outer shell of electrons, would need to gain an electron. It's going to appear as Cl negative. Use both those pieces of information or just one of them, but if you've got something that is positively charged, opposites attract, so this will be attracted to negative electrode, and on the other side, the negative part will be attracted to the positive electrode. So our copper, therefore, would be at the negative electrode. Copper would turn into a solid, so we need a solid on that side, and the negative chloride ions would be attracted to the positive electrode, where they would pick up an electron and turn into the chlorine gas, which gives you A as our correct answer. Dealing with salts, salts are formed during neutralization reactions. What will happen for a lot of these questions is they'll play off the fact that acids and bases are involved in making a salt. It doesn't mean that they will be the salt itself. A couple pieces of information. First thing, bases will tend to be metal oxides, hydroxides, and carbonates. They'll tend to be metal oxides, hydroxides, carbonates. That can rule out A and C because they're bases, which is not what we're talking about. When we have the endings of nitrate and our ethanoate, the nitrate could come from using nitric acid. However, the trick with this one is that is actually nitric acid. We have hydrogen and we have our NO3. That is nitric acid, meaning it's not a salt, but it could be used to make a salt. In potassium ethanoate, the ethanoate part means that ethanoic acid was neutralized. And that could be neutralized with something like potassium oxide, could be hydroxide, or it could be carbonate. Just depends, but that is the only one that would be formed in a neutralization reaction from an acid and a base, forming the salt that we've got there. Next one, we've got to think about ammonia. Ammonia is basic or alkaline. This means it's going to form something with a pH above 7. This would make it acidic, not it. This would also be acidic, not it. This would be neutral. If ammonia did not dissolve in water, that would have been the correct answer, but it does, and it will form an alkaline solution which has a pH above 7, and that's the only above 7 number we have. Next one. We've got the product of combustion being looked at. We have a gas being burned, and a colourless liquid was collected in the cooled test tube. There was no change in lime water. Lime water turns cloudy if there's carbon dioxide. The fact that it doesn't change in this example means there is no carbon in the fuel that's being burnt. Methane, we should know, is a hydrocarbon, which would form carbon dioxide and also water. So it's not that one. Our CO would form carbon dioxide. It's not going to be that one. Hydrogen would form only water when it burns, which means that is going to be a correct answer. That would be this clear liquid that's found in here. And ethane also has carbons and hydrogens. Therefore, that will not be the correct answer because that would make carbon dioxide. On to number 11. We're looking to see which things have the highest boiling points. First thing, we need to identify which chemicals we've got. Each of them have 4 carbons. 4 carbons in chemistry means we're talking about the buttes. There are quite a few options of the buttes in this page, so let's look at how we can tell them apart. First thing is, the first one has only carbon to carbon single bonds. This means this is going to be an alkane. Specifically, that will be butane. Next up, we have an alkene because it has at least one carbon to carbon double bond. That will be but. We need to know specifically that it's but1ene because of the position of the carbon to carbon double bond. Next up, the COOH, C double bond OOH or Q, means that that is a carboxylic acid. Carboxylic acid would be butanoic acid. And then next up, we have an alcohol, butanol, which is the one that we're wanting to deal with there. This means the highest value is going to be butanoic acid. And that would be our correct answer, which is C. We've got 2 properties of these chemicals. First thing, it decolorizes bromine water. This means it must be unsaturated and have a carbon to carbon double bond. I would deal with that information first. So A does not have that. B does not have that. C and D both do. So they're still within the running. Next up, they're forming an acidic solution. In these chemicals here, we need to be able to recognize that this is a hydroxyl group, making it an alcohol. Whereas for D, we have a carboxyl group, making it a carboxylic acid. Then it's not too far of a stretch to say, well, that has to be our correct answer, because that would give us our acidic part, because it's a carboxylic acid. So D is correct for question 12. On to question 13. If you're asked about general formula, I would always just go straight to counting them up. We have C3H6 and then an O. We have C4H8 and then an O as well. If you look at the connections between them, I'm spotting that it's double. The hydrogens are double the number of carbons. If that follows through, then C5 would be H10 with an O. When you count them up, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That does work. That means B would have to be a correct answer. If you write these down, it saves you counting them again and again and again, getting yourself confused. Count them carefully, write it down, and then see which one follows that pattern. Next up, we're asked about a formula mass of a cycloalkane. This means it has a ring of carbons. Get our ion, I would go for the smallest one that we can. 3 carbons will be the smallest we can have. So I'm drawing cyclopropane. Each carbon at the moment is making 2 bonds, which means each of them need 2 H's on them. So this would be C3H6. We then want to see how heavy these are. We have 3 carbons. We have 6 hydrogens. We'll double check what the masses are. Carbon is 12. Hydrogen, hiding down here, is 1. We have 3 times 12, which would be 36. 6 times 1, which is 6. Give you an answer of 42. That is an option for what we've got, therefore it's a correct answer. If this didn't fit, we could then look to use a slightly bigger cycloalkane. So you might go to cyclobutane. Can't get any smaller for these chemicals because 3 is the smallest shape we can make. But for other ones, you might want to get bigger or smaller. Just follow your values. So if all the values were quite a lot bigger, you maybe want to add another couple of carbons just to get the right answer. Next one, we're asked about metallic bonding. There are 4 different bonds and structures you need to be aware of. In our metallic one, we have positive ions and a sea of delocalized electrons. That means A would be correct. B, we have negative ions and negative electrons. These would not attract at all. Those would repel one another, which means that just doesn't work at all. For negative ions and positive ions, that would be ionic bonding that we've got there. And a shared pair of electrons means we're dealing with the covalent type of bonding in that. So A is our correct answer for this one. On to number 16, we're asked to find something that has a density of less than 3 grams per centimetre cubed, and it also has to withstand temperatures up to 600 degrees. Dealing with the density first, A has a density less than 3, so does B. C and D are both out. We need to have a metal that doesn't melt before 600 degrees. If you used A, you'd be rising the temperature up, and as soon as it gets past 98 or gets to 98, your aircraft is going to melt, which would be an unfortunate turn of events. This means that we want one that has the higher melting point, because we're wanting it to stay as a solid in this case. There may well be questions where we want it molten, so you'd be looking for a melting point lower than the temperature they give us. But unless you want a liquid aircraft, which this question definitely does not want, you're looking for the one that has the higher melting point and the density less than 3. Given as B. Next one. Which of these metals can only be extracted from its ore by electrolysis and forms an oxide that isn't insoluble in water? I'll deal with the first point first. If it's only extracted by electrolysis, it must be very reactive. For it to be very reactive, we can check that by looking at page 10. So it's high on page 10. Question asks us about calcium, aluminium, copper, and lead. Looking at the ones that are up near the top, that would bring me down to calcium and aluminium. This means I can rule out the other two. When you're checking if it's insoluble in water, you want to go to page number 8. And we're looking for those metal oxides. We have aluminium oxide, which is insoluble. We have calcium oxide, which would be soluble. That means that aluminium would be our correct answer. If we look at the lead one, the lead would satisfy the point about it being insoluble metal oxide, but it doesn't fit the only extracted by electrolysis. Things that are lower down, such as the lead, could be extracted by heating with carbon or carbon monoxide, meaning that A has to be our correct answer, because it fits both categories, not just one of them. Next one's talking about electron flow. Electrons flow from more reactive to less reactive, or from high to low on page 8. We have aluminium and nickel. We already saw that aluminium is quite high up, so would be what I would be thinking we're doing. Clear this up. We have aluminium and we have nickel. So we'll go from aluminium to nickel. Let's rule out any ones that say the opposite. So by B, by C. Next up, if we've got electrons flowing, electrons flow through wires. So anything that doesn't say anything about it going through wires is wrong. And A would be incorrect. It talks about electrolyte, which is a solution. That's not what happens. But we do have electricity going through those parts. Next one, we've got which metal, when paired with magnesium, would produce the highest voltage. I've heard a few ways of people explaining how to deal with these questions. I would always talk about them being further apart. So the further apart two chemicals are, higher the voltage. In this question, we are talking about magnesium is the one that's set. So we'll put that in here. So we have our magnesium there. We're asked about iron, lead, tin, and zinc. For the highest voltage, the furthest apart, that means that lead would be our best option for getting the highest voltage. Now, lead would be B. Next up, we have got two half cells. We're producing electricity with two half cells joined by an ion bridge in the middle. We are asked to give the overall redox reaction for this cell. First thing I would do is just get to grips on which one's an oxidation and which one is the reduction. To do that, I would go to the data booklet. Bromine was one of the chemicals asked about, and we can find bromine here. In this version of the bromine, we have the electrons on the left hand side of the equation, and it tells us up the top here that these are reduction reactions. When we go back to what we've got, that is indeed what we have. This means that our bromine is undergoing a reduction reaction. Instantaneously, because it's redox, we need an oxidation in the other chemical. We have the electrons on the right hand side this time, which means they are opposites. We have one that's being reduced and gaining electrons, one oxidized, losing electrons. Moving on, next thing we need to do is check, do we have the same number of electrons in each of them? We have our bromine gaining 2 and our sulfite turning into sulfate. We have 2 electrons, so that works fine. Next, we need to combine these 2 equations together. What I like to do is imagine there's a line down the middle that separates my left-hand sides and my right-hand sides. We're looking to see, is there anything that appears on both sides that we don't need to include? Well, electrons appear on both sides. Double checking, everything else is different. Either it's different chemicals, it might have lost its charge, it might be a different state. Anything that's exactly the same, chop away. So we need to just follow them through and see which ones would be a correct answer. We got rid of our electrons. That means that A cannot be correct. Any other ones like that? No. Next, we want the bromine Br2 on the left. This has it the other way around. So B is ruled out. C is looking good so far. We have our Br2, SO3 2 minus, yep. H2O, correct. 2Br minus, yep. SO4 2 minus and H plus. That's looking awfully good. And in the last one, there's no H pluses and there's no waters. And that would be why that one is incorrect, leaving us as an answer of C. Next one, number 21. Given a polymer and we're asked to turn it into a monomer, we want to reform the molecule it was made from. We want to reform the carbon-to-carbon double bond. What I would do in these questions is we're going to be splitting them up like so. Now I can cheat ever so slightly in this and get rid of the parts here. Now, once I split it up, so I've only got one of the repeating blocks, I want to then put in a carbon-to-carbon double bond in here. When we're looking at these, we want to make sure that we have a CH3 and in this thing here with the C double bond O and CH, they need to be on the same carbon, and the other carbon has to have 2 hydrogens. When you look at A, it might not immediately appear that that is actually the same. All that's happened, it's been flipped around, and because it's been flipped around, it still has the same bits connected to each carbon. That means A is going to be our correct answer. When you look at B, B doesn't have a CH3. That cannot be correct. Next one, again, we don't have a CH3. We also don't have a carbon-to-carbon double bond. So that cannot be a monomer. And then D cannot be because it's not got a carbon-to-carbon double bond either for that. C and D would be ones I'd rule out the quickest because there's no carbon-to-carbon double bond. And when you're left with these 2, A fits because it's got the correct things attached to the same carbon, even though, like I said before, it's flipped round. Next one, number 21. In question 22, you need to know about 2 processes that are involved in making fertilizers. You need to know about Haber and Oswald. Haber produces ammonia and Oswald produces nitric acid. And where it gets tricky is that is using ammonia. So ammonia is involved in both of them, but it's produced in Haber and used in the Oswald process. We're asked about the product for the Oswald process, which means we care about nitric acid. Ammonia is NH3, nitric acid is HNO3. That means that these 2 ones have to be ruled out from that. In terms of the catalyst, the Haber process is the iron catalyst. It does come first alphabetically out of the 2. So there's Haber versus Oswald. That's any help to you at all. That means that we do not care about iron in this question. It does have a platinum catalyst. Out of space, but platinum catalyst. And that would be B, our correct answer. So we can do it from a ruling out point of view, or we can just know that it's nitric acid and platinum for Oswald. Next one, we're asked about radioisotopes. We are comparing same radioisotope in different environments, half-life is unaffected by anything. If it's the same radioisotope, it will have the same half-life. Doesn't matter if it's a solid, liquid, if it's in a compound or on its own, it will still be the same value for all of them. That makes C our correct answer. Next one. An isotope, radioisotope used to monitor blood flow around the body. To prevent damage to the body, it must be able to escape through the skin. Alpha is easily stopped by paper. If it's stopped by paper, it would be stopped by the skin. This means that alpha would be no good in this particular situation, which means we would want beta or gamma. In this case, we've only got beta. Has to be beta. If it's going to be in the body, you want short half-lives. You do not want it to stay radioactive, kicking out radiation for longer than necessary. This means that our correct answer has to be C. There are some situations you do want it to last for a long time. You'd be looking for a half-life that's a bit longer, or you might want something that goes through a lot more things. So gamma is the most penetrating. It will go through more, stopped by thick lead. In some situations, that's a good thing. Here, D is the best option. This one, here, we are measuring out volumes of sodium hydroxide for a titration. They've used a measuring cylinder, which isn't ideal. For accuracy, we're wanting the more fancy types of equipment. Beakers are not particularly good for measuring things out. There's a lot of error included in them. Measuring cylinder as well wouldn't really work. Conical flasks we tend to do our experiments in. Pipettes and burettes are more accurate than your measuring cylinders and beakers. I sometimes explain it as the equipment that you would have been used or you would trust S1s and S2s with tend to be less accurate. Accuracy comes with price, so the more expensive pieces of equipment would tend to be saved for people who are a little bit more mature and less likely to damage them. And pipettes and burettes are used in titrations, would be another approach you can do from them. Continuing on with the nuclear chemistry idea, we are asked about which type of radiation is emitted from an equation that they've given us. We have two types of equation we can deal with. We have alpha, which would be 42He. We also have our 0 minus 1E, which is our beta. If it's gamma, gamma is just energy being released. There's not a particle being given off. So we only need to know about these two. Here, it's the electron one, which means it's going to be beta as our answer. Next, we're asked to name the element that we've got left over once it's emitted. It's beta particle. We have got to think about our top numbers and bottom numbers. Here, we have 131. There are no change here because it's still 0, which means our Y has to have a mass of 131. On the bottom, we're trying to solve this kind of little equation. We have got 53. 53 equals something minus 1. With beta decay, the atomic number goes up by 1. Is the only number that makes sense in this would be that this is 54. Because 53 does equal 54 minus 1. So what we want to then do is go to our data booklet. We want to find out which chemical has an atomic number of 54. Now, check on this one. I said earlier that you could use either of these pages, so 6 or 4. And luckily for me, this does have our xenon, which is going to be our correct answer. If you can't find it on there, so if it was a number that wasn't present there, so if you look here, we're missing values, you'll find that on the full data booklet up on page 4. It just might take a little bit longer because there's more. All the elements are up on page 4, whereas here it's a bit of a condensed version. Another thing you can do is if you look for iodine, first of all, it's got to be fairly close to there. Xenon is our correct answer, so let's pop that down, name it. I'm going to give the name rather than the symbol. We have xenon there. Next up, we have a half-life question. calculate the length of time taken for the radioactivity of xenon 133. We can get rid of those ones. To fall to 1/8 of its original value. In a question dealing with fractions, I would just say that we're going to start off with just 1. That'd be all of our radiation. After 1 half-life, we are going to be left with half of our original value. And each half-life is represented in my diagram as an arrow. And half-life's time it takes for it to half its activity. So we've done it once and we've got down to a half. So again, we get to a quarter. So again, we get to an 1/8. I have had to half this 1, 2, 3 times. A couple ways of doing it, and so the way I prefer it is to say, well, that's 3 half-lives. 1 half-life would be 5 days. So 3 half-lives equals 3 times 5 days. Gives you a total of 15 days being our answer. The other way you could do it is to say, well, it takes 5 days to go from there to there. Then takes another 5 days to go from there to there. Then takes another 5 days to go from there to there. So in total, you get 5, 10, 15 days getting to the same answer. Pick a way that works for you and just make sure you use the correct term from the table and then you'll get your correct answer, hopefully. Next one, suggest which of the radioisotopes would be responsible for long-term radiation. Well, this would mean, or this would suggest that we're looking for the highest half-life. So out of the 3, the highest half-life would be our cesium 137. Therefore, that would be our correct answer. Like that. Next one. We're asked here to complete a graph showing the volume of gas produced against time. The time we've got 0 up to 5. That would make me think that we're just going to do 0, 1, 2, 3, 4, and then 5, 6. So need to decide what we're going up in on the y-axis. So we need to get to a maximum of 48. Now, instantly I'm thinking 50 sounds quite a good value to get up to there. We've also got a little bit of help because we have been told that the value at time 1 is 32. So that would make sense that we go 10s up the way. So 10, 20, 30, 40, 50, that could be 60. And then each little box has to be 1. So to check that, you have 2 options. We can either say, well, there's 10 boxes, and that equals 10. So if 10 boxes are 10, if you scale that down, then that means that 1 box is 1. Another option, which I, to be honest, prefer, is just to think. So I'm looking here saying I think it might be 1. So just run it up then. If that's 0, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That works. And you can kind of experiment to see what numbers work out quite nicely. I will keep my 0 in there. Next, I'm just going to go through and plot out the other values. What I'm doing is I'm running up the number 2 line, because our next point has to be on that line, and we're going up to 40. Now that's quite nice because we've actually got the value just straight up there. And I want to get a point in where those 2 cross over. And I'm going to stick with little crosses like so. Then next up, I'm going to do the same for 3, 4, and 5. So time 3, we're at 46. Time 4, we're at 48. So that's 2 boxes down from 50. And then it keeps going from there onwards to here. In this situation, what we are not wanting to do is we do not want to do a straight line between each of the points. We want to try and get a nice smooth curve that goes through all of them. Now, this may take me a couple of attempts. You will only see 1 attempt and it will look amazing. Don't look too closely at the graph. We have the points in the correct place. We have it going up in a nice curve and flattening off towards the end. Try and make it a bit more smooth. Just take your time, make sure you get them as close to each point as possible, And then if it looks like a curve, draw a curve. If it looks like a straight line, do a line of best fit, and that would pick up your marks. In this question, we're asked to calculate the average rate between 1 and 4 minutes. Average rate, data booklet tells us, is change in quantity over change in time. Here we're dealing with 1 and 4 minutes. In terms of the quantity, we've gone from 32 up to 48. Well, 48 minus 32 gives you a difference of 16. And at the top, got a difference of 3. It's taken 3 minutes to make the 16. So when we pop that into our equation, we get that will equal 16 divided by 3. Popping that into the calculator gives us an answer of, I would round this to 5.33, and that is, as the question says, in centimetres cubed per minute, like so. And that picks up your 2 points that we've got for that one. Just a different measurement that could be used to follow the progress of this chemical reaction. If we're talking about a gas being given off, that will reduce the mass. So we could deal with the mass change that we could deal with in that one. We have an acid, I believe. Let's have a look. We're making an alkali. We could follow the pH would tell us the change as well, because it will increase above 7 or when the product's being made. So we can look at the change in pH. Would be another one. We can also look at the concentration, because you're going to be changing the concentration of the calcium hydroxide as well. Would be another one. My main two ones though would be the volume and the mass would be the main ones I would head towards. Here we are repeating the experiment at a higher temperature using the same mass and same volume of water. All that the temperature is going to do is going to speed up reaction, but it's not going to change how much stuff we're going to get. You're baking a cake and you put the oven on at a higher temperature, you don't get more cake. It just takes a shorter period of time to get there, assuming you don't burn it. But the idea stands that you will not change how much product unless you change concentrations or masses of the chemical that we're using. The final mass in this one was 48. So it'll be the same value. It'll still be 48 centimeters cubed. And this one, I asked you about the time it takes to get to 48. It would be a shorter time, if that was the question. Next one. One of these, read through the passage and then answer the question that follows. You would definitely always read through it. Never, well, I would actually just go to the question first. State the name of the two products formed when DEF is heated in the exhaust system. DEF, heated, I'm looking for the word heated here. So that's the paragraph we're dealing with. Urea reacts with water to make ammonia and carbon dioxide. Products are formed, products are made. That would therefore be ammonia and carbon dioxide. Next, calculate the mass of urea in kilograms used to make 5 kilograms of DEF. So the values we've got, we are told that 32.5% of the DEF is urea. Okay. So we've got 32.5% of DEF is urea. Then we're trying to get, we've got 5 kilograms of DEF, so we're just looking for 32.5% of 5 kilograms. I would usually do percentages. If we're using a percentage, I would do 32.5 over 100%, out of 100 times 5. Go to our trusty calculator, pop that in, and we get 1.625 kilograms. You might want to round it to 1.63, but I'm just going to leave it as is to get the answer. Here, the harmful gases in the exhaust fumes, if released, can dissolve in water to form a solution that is, whenever we talk about hydrogen ions and hydroxide ions, talking about acids, alkalis, we may be told up here something to do with that. So harmful gases, exhaust fumes. Here, got our two exhaust fumes. So we have nitrogen monoxide and nitrogen dioxide. Nitrogen is a non-metal. You're unsure about metals and non-metals. Remember, like we did earlier, you could use this page, page 4 or page 6. Nitrogen is number 7. On the right-hand side of the line, meaning it's a non-metal. And we should know that non-metal oxides dissolve to form acids. And as long as it dissolves in water, which it will do in this case, because it tells us that we have. If you were asked about alkalis, that would be soluble metal oxides. And the second part to this is an acid contains more hydrogen ions than hydroxide ions. Something that helps me is if I think of an acid, I think of hydrochloric acid. The reason it helps me is, well, it's got a H. That would be H+. And they say a menace. So that's the hydrogen ions. It's an acid. And also chlorine's a non-metal. Hydrogen's a non-metal. So non-metals make the acid. So hydrogen chloride or hydrochloric acid is the one that helps me dealing with these questions. Next, we're asked to state why it's not, the DEF is not considered a dangerous substance. DEF is preferred because it's not considered dangerous, it's not toxic or flammable. So you could pick one of those two that we've got. It's also easier to store, did it say? Yeah, easier to store. So I'm going to go for not toxic. You could talk about the flammable part if you wanted to. Or, yeah, not toxic or flammable. Be your two ones that we're dealing with here. Asked about uses of fertilizer. Urea is a single nutrient because it only got one of the elements necessary for plant growth. So we need to be thinking NPK, nitrogen, phosphorus, and potassium. If this other one is not a single nutrient, that means it has to have multiple of the nutrients. Got N and it's got P. It contains nitrogen and phosphorus. It's got two of them that are involved for that. That's it. That's what you do there. Percentage by mass, data booklet tells us percentage by mass equals the mass over the gram formula mass times 100. In this type of question, what I've clocked is that there's hydrogen appears twice. What I would want to do is I want to expand this out and squash things together to make it just easier to deal with. So what I mean by that is, well, we've got nitrogen inside of the brackets with a 2 outside. That means that we've got to have 2 nitrogens. When it comes to the hydrogens, there's 4 of them inside the bracket. Bracket on the outside, that would be H8. We've then got our H, our P, and our O4. To make this even easier, I would then make it N2, H9, P, O4. We need to then work out the GFM like we've done before. Drag it along. There are 2 of them. 9 of them, 1 of them, and 4 of the auctions. We can then go to the data booklet and look these up. Nitrogen will be 14. We have nitrogen, we have hydrogen, we have phosphorus, and we have oxygen. Here, so 14, 1, 16, and 31. Means we've got 28, 9, 31, and then 64. Pop this in the data, pop this in your calculator. It gives you 132 as the GFM. Next up, what we want to do is we want to decide or look at which chemical should we be focusing on. We need to focus on the nitrogen. And the nitrogen that we've got, we have 28 as our mass of nitrogen. So we pop this in using 28 on top, divided by 132 times the 100, and then we can pop that into our calculator and get our final answer. Here, I like to round to 3 significant figures. So what I'm doing is I'm looking at the 4th number, which is a 1. That would round down. So 21.2% would be my final answer. One of the common mistakes that I would expect to see from people in this type of question would be to think that they're only using one nitrogen at the end of it and just looking at just that single nitrogen, which would mean they'd put 14 on top and it'd be 14 over 132, which would half the percentage. I would always recommend try and just figure out how many of each there are, taking into account brackets and any things that appear more than once, and then you just follow it through and get your answer. On to number 4. Here we have a carbon to carbon double bond breaking. We're putting on something else, in this case hydrogen bromide. That means that is an addition reaction. When you break the carbon to carbon double bond and you put new things on there, that's an addition reaction. We're now asked to show the outer electrons joining together for hydrogen bromide. First up, we want to go to page number 6 and see how many outer electrons do both of them have. We've got 1 for hydrogen and we've got 7 for bromine. Hydrogen needs to make 1 bond, bromine needs to make 1 bond, so this should be quite straightforward. We have hydrogen here, and that has 1. With the bromine, I find it easiest to just go round like in a compass, north, east, south, west, keep going until you run out, which I now do now. We have then got this point here that needs to join on. We have this point here that needs to join on. So I'm now going to orientate them to point towards each other. Got my hydrogen there. I'm going to take my bromine here. Got the hydrogen's electron going in first. This next electron I'm putting in is this electron here. Then I'm going to fill it up with the other electrons remaining. Put my Br in there. You want to try and make sure that your crosses are inside or on the lines, and that will pick up your mark for that one. We're asked about which chemical can be reacted with ethene to form chloroethane. So we're going to try and figure out what we need to tweak about this question. Instead of bromoethane, we want chloroethane, which means we need to be replacing the bromine with a chlorine. Now to do that, instead of having hydrogen bromide, we're going to have had hydrogen chloride. And that would give you hydrogen chloride as your answer. HCl, otherwise known as hydrochloric acid. You could give either of those answers and still pick up the mark. It just depends on which way you want to do. Chloride part fits with the previous question, maybe makes it a little bit easier to deal with. But hydrogen chloride is the correct answer. In this one, we are trying to figure out an process that we will not be familiar with. So we have a bromine is being changed to this thing, a C triple bond N, and then we're turning into our carboxylic acid with the C double bond OH. In this question, we want to work our way back the way to figure out what the haloalkane that we would have used to make, in this case, ethanoic acid. You can either jump straight to from the end to the beginning, or we can do it in baby steps. So I'm going to do it one step at a time. First thing we need to do is we need to get rid of C double bond OH. And then that is instead now going to be a C triple bond and then an N. If we then go one step further back again, this time on the end we have got just bromine. And that would be our correct answer there. If you want to do it jumping all the way back, what we can see is that the Br is swapped directly for the C double bond OH. So we could have got rid of this and put our bromine in there, which still gets the same result of it. So the correct answer would be bromomethane, where you've got the bromine attached to the C and then the 3 H's. Rid of that. One of the things that people might miss is that you're actually adding on an extra carbon. So when you go back the way, you lose a carbon. So this carbon here would no longer be there. Just the way the reaction works. Next up, We're asked about a dilute solution of ethanoic acid. This is just a fact you need to know. That is vinegar. Question number 5 is the first of the 2 using your knowledge of chemistry questions. This one is about neutralization, indigestion, and chemicals used to neutralize. We're asked to figure out which of the 2 chemicals is the best at neutralizing an acid. First thing, we could talk about the fact that we have a base in our calcium carbonate. So something like bases neutralize acids. We have metal oxides, hydroxides, and carbonates are examples of bases. You could also add in the fact that soluble bases are called alkalis. We could then write down the general equation for neutralization, which is acid plus base forms salt plus water. If you have a carbonate, you also make carbon dioxide. We could then pick a specific acid that we want to react with the calcium carbonate. I'm going to go for hydrochloric acid. We have hydrochloric acid plus calcium carbonate makes calcium chloride, water, and carbon dioxide. We could add the same mass of the 2 different tablets to equal volumes and concentrations of the same acid, and we could measure the pH before and after. The one that would be most effective would cause a bigger difference in the pH values. Or what you can do is you could collect the volume of carbon dioxide produced. The one that is more effective would produce more carbon dioxide because it's neutralizing more of the acid. Use a gas syringe to collect the gas. And then again, the bigger the volume, the more effective it would be. You also repeat the experiments and then calculate an average to get a more reliable result. As with all these questions, you get 1 mark for a limited answer, 2 marks for reasonable, and 3 for a good answer. And this would hopefully pick up all of those marks. Next one, we're asked for a systematic name of this alkane. Here we need to look for the longest chain of carbons. You need to be careful in these ones because here the longest chain is 4. Where we go down and take one of the side carbons, not 3. This means that it's going to be based off of butane. If you picked 3 carbons as longest chain, you would be thinking it would be prop something. We have got butane. We have a 1 carbon branch off of the second carbon. That's going to be 2-methyl butane. Substance that burns to release heat energy in a combustion reaction is a fuel. Fuel is a substance that burns to release energy. Next up, we're going to balance this equation. I'm going to start off with carbon first of all. There's 5 carbons here, only 1 carbon there. To fix it, I want to put a 5 in front of the CO2. Next up, I would look at the hydrogens. There are 12 hydrogens on the left, but only 2 on the right. Fix that, I'm going to put a 6 over to here. We've got 2 oxygens in the O2. With it being 5 CO2s, we've now got 10 oxygens plus 1 in the water. Now there's 6 waters, so that's 6. Gives you 16. If you want to get the same number on both sides, if I put an 8 in here, 8 times 2 bumps this up to 16 as well. Then we get equal values on both sides. And that is that one balanced. Next question. Here we're asked to calculate the energy absorbed by the water. This means we're going to be dealing with EH equals Cm delta T. You see on page number 3. Page 3 can also help us with the specific heat capacity of liquid water. This question, we are heating up water, which means we are using the 4.18 that we've got there. So we're asked for EH. It is water, so it's 4.18. The trick for, or the thing to watch out for with M, is the mass of substance being heated. And we're heating the water by burning the isopentane. That means that we don't deal with these ones. We do deal with the 200 grams. We also need to turn it into kilograms. It's going to be 0.2 kilograms. As a kind of check to make sure you're doing the right thing, it says here it's kilojoules, kilograms, or per kilogram in degrees Celsius. So we need to be aware of that. So it's going to be 4.18 times 0.2 times change in temperature. Difference between these two numbers is 12. 35 take away 23 is 12. That means that EH equal, pop it in the calculator. So here our answer would just be 10, 10.0, 10.03, whatever one you want to pick. you've got 10 kilojoules of energy has been released. Next up, we have to draw our experimental setup that would allow us to carry out that experiment. So first up, we want some sort of metal can. Next, we need the substance that we're heating up. This is going to be our water. This question, you're going to need to be able to measure the temperature that we're getting to. We're going to have some sort of thermometer. That. Good thing is, if we label things, then we can excuse our less than ideal drawings of them. But there, got our chemical in here. Do they holding it above it in one or two ways? You could draw some sort of little tripod involved there. The other thing is you perhaps in class you've used a clamp stand to hold it in place to make it kind of sit above the spirit burner with the fuel in it as well. But we just need to make sure we can get the heat from the fuel, burning it, releasing it, and it goes into the water. For that, if you were making improvements, you could put a heat shield around it, so you've got 2 blocks on either side, and it helps keep the heat in and get it into the water, or something like this would be fine. Make sure you label it like it says, and then you should pick up both the questions here. Calculate the mass required to prepare 500 centimeters cubed of 1.5 mole per litre solution. We need to get used to recognising volumes in centimeters cubed and concentrations, moles per litre. We also want our volume in litres, and that will allow us to use them together. Data booklet tells us that N equals C times V. Find in here. That's concentration times volume. Let's do that. Put that in your calculator. That will give you 0.75 moles. Next up, the question wants to know the mass. The mass is to do with NMGFM, number of moles, mass, and gram formula mass. For N equals M over FM, rearranging this gives us the M equals times FM. M equals maybe the 0.75 we just calculated times NaCl. That means there's one sodium, sorry, and there's one sodium and one chlorine. Use the data booklet to find out how heavy the two things are. Chlorine 35.5 and sodium is 23. 8.5. Pop that into our rearranged relationship. Gives you 43 point. I want 3 values. 7 that comes next would go round up, so 43.9 grams is my answer for that one. Moving on. Piece of equipment used to accurately measure the mass of solid sodium chloride. Measuring mass is going to be your balance. Sometimes called a scale. Balance would be my preferred word for this. Next one, we're asked to calculate the average boiling point. For this one, average, we're talking about the mean here. I add them all up and divide that by 3. You need to watch out for how you type this in your calculator. What will often happen is the calculator will think, if you just type it all in, they'll think you only want to divide that last value, 108, by the 3. Isn't what I want to do. So brackets can be helpful. If you bracket off adding part, 7 and 108, close your bracket and then divide that by 3, you ensure that you get the correct answer, which would be 106.67 or 106.7. Present results in a table. In a table, quite some time in an exam question. So first thing we need to do, think of our headings. We've got our concentration of sodium chloride. I also want to make sure we put our units in little brackets. That's moles per litre. And on the other side, you've got our average boiling temperature or boiling point. That is in Celsius. Add 0.5, 1.0, 1.5. Because we've already defined the units, we don't have to write the units each time. Our values up, we've got 106.7. They gave us, that's the wrong place. That was the one for the bottom one, 106. 7, 104.0, 101.3. Just like that. Make sure you've got labels, units. Should be kind of rearranged decently. And yeah, that works out as our correct table. Next one. What type of graph should we show for this one? A general rule is that if there's numbers and numbers in the columns, a line graph or scatter graph would be the best. If there's words in any of the results, you'd want to use your bar chart for those. Suggest a conclusion for the results as concentration increases, average boiling point increases as well. Could do it decreasing as the concentration decreases, the average boiling point decreases. Make sure you do it in the order they say, so we're finding out how the concentration affects the boiling point. But deal with the concentration first, and then move on to the boiling point afterwards. Here we've got some flowcharts, and we're asked to identify which chemicals we've got involved. Dilute acid A. Well, we've got something plus magnesium makes magnesium sulfate. Well, the magnesium part's dealt with this. There's an acid that's to do with sulfur. That acid is going to be sulfuric acid. Next, we're asked to identify gas B. What I'm looking for here, well, I now know that it's magnesium sulfate we're making. Also know it's sulfuric acid. Magnesium is just Mg. Or sulfuric acid is H2SO4. We have a metal plus acid. We're trying to figure out what we make. Now, we always make a salt in this case. Now let's look at what we've got left. The magnesium sulfate would be MgSO4 plus something else. Well, the magnesiums are dealt with. The SO4 is dealt with. That leaves just hydrogen. And another way, if you just remember from your reactions of metals, that acid plus metal makes salt plus hydrogen. Gas B is going to be hydrogen for that one. Next up, we've got using a metal carbonate. I mentioned earlier that it performs carbon dioxide. That was in the using your knowledge question, which means that you'll see bubbles. It will stop bubbling. The gas is no longer produced, or you can talk about it bubbling or fizzing, something like that. But the reaction will be done when there's no more carbon dioxide produced. Next up, in all of these reactions, a salt is produced. State which of these salts would be produced as a precipitate. Precipitation is when a solid forms from solutions. Let's try and identify our salts that we've got. So we have got 4 options here. Got magnesium sulfate, barium sulfate, sodium sulfate, and copper sulfate. Looking at the data booklet, I'm leaning towards barium. Barium salts tend to be insoluble. Likes of copper sulfate is the blue solution you may have used at some point in your chemistry career. But we'll double check just to make sure that I'm saying the right one. Again, we go down to this page here. We've used it earlier, page number 8. We had copper sulfate. We had magnesium sulfate, both of which are soluble, so not our answer. Sodium sulfate, also not our answer. Barium sulfate is the only one that's insoluble. So check them in there. If it's insoluble, or it makes something that's insoluble, that will be the correct answer. My definition of neutralization is the reaction between acid and base forming water. That's just the definition that you need to be aware of. talking about isotopes. Isotopes have another definition. You have the same, so atoms with the same atomic number, different mass number. Next question asks us about group 8. Group 8 or group 0, the noble gases, all have a full outer shell of electrons. This is why they are stable. Full outer shell of electrons. This is why they don't need to go and react to get more electrons. Next one, we want a chemical equation using symbols and formula to show that reaction. Okay, so xenon hexafluoride is made. If it's made, it's at the end. By reacting xenon difluoride. Di, like carbon dioxide, is CO2. It's carbon into oxygens. So if we've got xenon difluoride, it'd be XeF2 plus fluorine. We need to be conscious of the fact that that is diatomic. That means that it exists as F2. If you just put F, you would be incorrect. There are 7 diatomic elements. A couple ways of knowing them. My preferred method is Hin Fockel Brew. The symbols for hydrogen, iodine, nitrogen, fluorine, oxygen, chlorine, and bromine. Another way you could do it, also go in a 7 shape from the number 7 plus hydrogen, or you might have another way of doing it, but anytime they're used in an equation as the element itself, you need to put a 2, F2, not just F. Next one, we have a solid at room temperature, a melting point of 49 degrees. Now that's going to be classed as a low melting point. Given any more information, formed compounds doesn't really give us more information. The fact that it's low melting point, though, there's need to be aware of 4 different types of bonding and structure. You have your bonding, have our structure. So metallic lattice, ionic lattice, covalent network, and covalent molecular. Now the only one of them that has a low melting point would be your molecular ones, your covalent molecular. This question only asks us for the structure. So the structure we'd want to use would be molecular. If you said covalent molecular, that would still count. They are asking you specifically about the structure. So you should go for molecular as your answer. Next up, we're talking about how much of the chemical is needed to catalyze it. Catalysts are not used up. That means there would be 35 grams remaining, the same as at the beginning. There's none been used up. Calculate the cost, purchasing required mass of the catalyst. If it's 10 grams, is £69.40. Right, we'd lay this out a little proportion. So if 10 grams costs us £69.40, and we want 35 grams. When you're looking at these, you should spot that we are using more than 10 grams. This means that our value in price has to be higher than that. If you end up with a value that's smaller, you've messed it up. You need to start again. What I would think about doing is getting to 1 gram. How much would it be for 1 gram? Go from 10 to 1. We want to get it smaller, so we're going to divide by 10. Any number divided by itself gets you to 1. You go from 1 to 35 times by 35. We want to do the same on the other side. Divide by 10 times by 35. Take our calculator, 69.40. Divided by 10 times 35 gives you £242.90. Looking back at this question, I've been caught out by the fact that it's saying you can only buy them in 10 gram tubs. What I was doing was working them out per gram, but we're not allowed to do that. So that means I need to rethink this. So what we need to do is jump away and think, well, actually now, we only need 35 grams, but we closest value we can get would be 40 grams. We need to scale it up, thinking about buying 4 tubs of 10 grams rather than just saying how much we need. So just showing how important it is to actually read through the questions properly. Change my colour. I got that muddled up. So we want 40 grams. That means that we're going to need 4 times the price because we're buying 4 of those tubs. So it's going to be 4 times 69.4 this time. Four times 69.4 gives us 277.60 pounds. So yeah, reading the question, that caught me out. Yeah, just watch out for it, and then hopefully you will pick up and won't get as confused as I did. Next one, we're asked for another definition. Here we have a family of compounds that have the same general formula and similar chemical properties. Next up, we're told about different classifications of alcohols, things called primary, secondary, and tertiary alcohols. First question is just asking for the functional group present in all of them. That is the OH group. We're wanting the name, which is the hydroxyl group. Carboxylic acid, it would be carboxyl. Structure shown, and we have to identify the classification of this particular chemical. Goes up and tells us it's all to do with how many hydrogens are attached to the carbon bonded to the functional group. And they've circled, in each case, carbon has the OH attached. Let's do that for ours. We've got this carbon here. Then it's all to do with, the question says, how many hydrogens are attached to that carbon. We have only got 1 hydrogen attached to that carbon. And if you look up to here, one hydrogen attached to the carbon with the OH makes it a secondary alcohol. Down here, and that is going to be secondary. Next, we have to change this around to make it have a different classification. Classification based off of how many hydrogens are attached. What we're wanting to do is I'm going to move H. I'm going to put it here instead. Doesn't ask us for this, but this would then make that a tertiary alcohol because there are no hydrogens attached to the carbon with the OH. So that's like the bottom one that we've got there. Good. Another one you could have done, you could have made it a primary version where you move the OH one to the left. That would be primary because there's 2 hydrogens attached to the carbon with the OH. Next up, asked to test for oxygen. Oxygen is tested by relighting a glowing splint. If it asks us about hydrogen, that burns with a squeaky pop. Mentioned it earlier, but carbon dioxide turns lime water cloudy. Those are your 3 main gas tests. Potassium chloride showing the charges on each ion. This is described as being the ionic formula. Do the same thing, put it that way around. A couple of approaches. The first way we could do it is look at potassium. Potassium is in group number 1. 1 electron in its outer shell. It would need to lose that 1 electron. When it loses that 1 electron, it will then become K positive. Other option would be looking down here. You've actually got potassium here. It says it's in K plus as well. Do that first of all. Chlorate. If it ends in 8, you might find it on page 8. However, chlorate is not found in here. But what we can look for is, well, if we've got a 1 plus charge on the potassium, then the other part of it has to balance that out with the negative charge. It will have to be ClO3 negative, because then they balance out. If you had something that had needed 2 potassiums, then whatever the other thing would be would have to have an overall charge of 2 minus to cancel out the fact that we've got 2 K pluses. So we're looking at making it neutral overall. There's no charge showing. One of the bits needs to be positive, one of the bits needs to be negative, and that will balance it out. Another definition, exothermic, it's a reaction that releases energy. Next one, we're asked about a flame colour. We're looking for lilac flame colour. Go back to page number 6. Lilac, again, is potassium. So because there's potassium present, then that's why you're getting a lilac flame. Next up, we're asked to calculate the mass of oxygen required to react completely with 2.25 grams of glucose. We're going to start with the glucose. we have a mass. We're doing NMGFM. Mass is 2.25. Number of moles we don't know yet. GFM we can always work out. We have 6 carbons, 12 hydrogens, and 6 oxygens. Carbon is 12, hydrogen is 1, oxygen is 16. You can get them from the data booklet if you don't remember them from earlier. 72, 12, and 96. Gives you a total of 180. Data booklet states that N equals M divided by GFM. That's what we're going to do now. That means it's going to equal 2.25 over 180. Gives you 0.0125 moles. When you're dealing with two different chemicals, you're going to want to look for some sort of ratio in an equation. Glucose to oxygen. There's no number balancing it. That means that's a 1. There is a number, that's our balancing number. It's a 1:6 ratio. That means if we've got 0.0125, we need 6 times as many on the other side. I'm going to take my answer, times it by 6, 0.075 moles. And then last up, we were looking for the mass of oxygen. That means we are dealing with NMGFM again. Told the moles. M equals what we want to know. GFM. Diatomic. So it's 2 times 16. If you got that wrong, it's going to mess up your answer. That's 32. So if N equals M over GFM, then M equals N times GFM. Means we've got 0.075 times 32. Here, times this to get a final answer of 2.4 grams of oxygen. What is required? Next, we're asked to describe the trend going from sodium to chlorine. We need to check where they are. We have sodium here and chlorine here. As you go across, the values are getting smaller. So covalent radius decreases. Next, we're asked to describe the general trend as you go down the group. As you go down a group, that's the up and down the way part, the numbers are getting bigger. That means it's going to be increasing. Covalent radius increases. And the reason that it's saying a general trend for this one, just a wee aside, you looked at this group here. We have it going up from bromine to, going up from boron to aluminium, but then down to gallium, and then back up again. So generally it is going up, which is why they're asking you for that. Predict a value in picometers for strontium. We spoke earlier and said that as you go down, it's going to get bigger. So we need a number bigger than 174. Is there a pattern that we see? Well, the first jump from here to here, we've added on 41. From here to here, we've added on 34. It's likely to be a smaller value again. There's a difference in the differences. So 41 to 34, that's a difference of 7. I'm going to take another 7 off to call it 27. And then I'm going to do 174 plus 27, because it's going to be bigger than that. That'll give me 100, 201 as my answer. And 201 picometers. Calculate the distance between the two nuclei in bromine. So bromine, we are told the radius is 117. If the radius is 117, then we want to use that again. We need 2 of them, because it's going to be 2 of the radius for that. So add them together, that gives you 234 picometers as the correct answer for that. Next up, we're talking about sodium ion, and we're looking for the electron arrangement. Sodium's electron arrangement is 281, which we get from the data booklet. When it becomes an ion, though, it's going to lose one of its electrons, the outer electron. So just the sodium atom would be 281. So our Na plus, after it's lost its outside electron, just be 2, 8. And that gives you there. Suggest a reason why the sodium ion is smaller than the radius of the atom. You look at the differences, but the only difference I've got is that there are less electron shells in the ion. That could contribute, it does contribute, but it could contribute to the size being different. Our final question is the second using your knowledge of chemistry question. We're asked about redox reactions. Redox reactions involve a reduction and an oxidation, as it says. We could talk about oil rig, which is oxidation is loss of electrons, reduction is gain. And then redox, they're happening at the same time. We could pick some half equations to put down. Remember, that will be found on page number 10. Typically, something like copper and maybe magnesium are good ones. They're used fairly often. So we would copy them down. Electrons flow from high to low, which means that the higher, more reactive metal will lose electrons and be oxidized. Magnesium is oxidized, copper is reduced. Could draw an arrow to show the way the electrons are moving. That we could then write down our oxidation of the magnesium. We want that to be the back to front version of what's in the data booklet. We are starting with our magnesium solid. That's going to give up 2 electrons, become magnesium ions. So we've got our 2 electrons, and then for our copper ions, in solution, pick up those 2 electrons, and then that will become a copper solid. The redox equation, we would cancel away the electrons, so we'd be left with our magnesium solid plus our copper ions goes to magnesium ions plus our copper solid. The ionic solution is an electrolyte. The electrolyte completes the circuit. You could talk about the electrons flowing through the wires. Electrolytes complete the circuit. Talk about, same as I said earlier, further apart, higher the voltage produced. Then say must be different metals. It can be implied from the fact that you need to be them farther apart, but they must be different to produce electricity. Possibly more things you could talk about, but this would be enough to get your 3 marks for being a good answer, 2 marks if it was reasonable, and 1 mark for being limited. That brings us to the end of the paper. That's how I would have approached each question, making sure that we read the question carefully so we avoid any little traps that may have been laid. Thanks for watching. Goodbye.